Yeah, so today I'm going to talk to you about a little bit of a correlation spectroscopy technique called RICS. This stands for Raster Image Correlation Spectroscopy. This was started to sort of try and translate what was traditionally done in single point by FCS to images, basically. So what are the major benefits of using RICS starting for this? So it can be used on any commercial microscope. So this is important because traditionally, before the coming of RICS, you needed specialized instrumentation to be able to do FCS. So it wasn't so mainstream yet. And it can be done with both analog system and photon counting system, as long as you take care of the characteristics of the detector. And it can be used to measure diffusion coefficient of diffusing proteins, diffusion modality, concentration, and so on, the same as FCS, but from images. This is very important. So let's see how it works. To understand how it works, we have to first understand how an image from a laser scanning microscope is constructed. So this is your outcome image, which is composed by a number of pixels. But how are the pixels put there, let's say? So this is a laser scanning. So that means that we are illuminating one single point at a time. And then we are collecting the fluorescence intensity in that specific point. And we are scanning this point through the image in order to get the spatial information, right? So basically, we move our illumination spot from left to right, and we collect the information along this line. Then we put it back, second line, and so on and so forth, and so on and so forth, until all the image is reconstructed. And then we go back to the first point, and we do it again for the second frame, right? This is different from like a camera-based system where this is done at the same time. This is done one point at a time. Some advantages, but this is not the point. So the point is that here we have a space and time structure in the image that basically, because it takes some time to move from one pixel to the next, from one line to the next, okay? These are the two important parameters that you need to take into account for RICS. How much time it takes to go from one pixel to the next and from one line to the next. A couple examples. So while you are imaging, molecules diffuse in your image, right? So proteins diffuse, you have your fluorescent tag, so you can track them, right? So let's assume that we have slow diffusion, right? This is an illumination spot of the first pixel, second pixel, third pixel, fourth pixel, and so on. So if you compute the spatial correlation here, you will have high correlation between adjacent pixels, and then it will decay over time. If the diffusion is faster, is much faster, it will lose correlation faster because the molecule diffuses away, but it will actually have this characteristic long tail because you will catch up with the particle while it diffuses during the scanning process. So these are two like characteristic shapes, let's say, of the correlation function that you get from RICS. But let's take one step back and see how this is calculated, right? So similar to FCS, where you shift the time trace over time at a certain delay, here is the same thing, but it works in space, right? So you take your image, you shift it one pixel to the right, compute the function, and then you shift it another point, and then another point, and then along the lines, and so on and so forth. So let's see. Well, let's skip this. And basically, once you have, since your data will be very noisy, you typically collect a number of frames. You compute the spatial autocorrelation function in every frame, and then you average all the information to get an autocorrelation function that looks sort of like this. So, as I mentioned, an image has a spatiotemporal structure underlying that is due to the way it is acquired, right? So the problem is that it's a bit, it's not the same thing, right? So if you think about space, right? If you take one pixel and the next the pixel to the right, the pixel to the left, the pixel to the top and the bottom, they're at exactly the same distance, right? Because that's how the scanning works. But the time is not, right? So if you take the pixel to the left, it's collected at the earlier time. To the right, it's a later time, and the pixel at the top is a much earlier time because it's the previous line, right? So this is not contiguous as the space is, right? So you have to take account of this. And instead of FCS, where you compute temporal correlations, here you compute spatial correlation. And since it's an image is 2D, we have two shifts, right? A shift along the X and a shift along the Y. But the formula is pretty much the same. And since it's a lot of operations and you want to do it within like your lifetime, it's important that this can be implemented through FFT methods as much as FCS is. So actually the computation is really, really fast. Also, FFTs are very easy to parallelize, accelerate with GPU and so on and so forth. So we are covered on the computation time. And then, but we have to know how space and time are connected in the scanning process, right? So our function is actually composed by two terms. We have a term that's used in the scanning, this S, and a G that is due to the diffusion process, right? So the G is similar to the autocorrelation function, let's say, this is the model for phase diffusion 3D, that you use for fitting FCS, right? Although instead of like time, we have parameters that relate to space because our time is encoded by space. And then we have a scanning term that takes into account the parameters of the scanning, right? And these will yield a 2D function that basically has all the information about diffusion. It's easier if I show you. So let's say that we're taking an image of very slow beads, okay? So this is what we get. We get the blur, these are beads, or whatever. They're pretty much still compared to the diffusion time. The scanning time, right? Because here we're sampling pretty fast. So these appear immobile. In fact, if we compute the autocorrelation function, this is perfectly circular, as you can see. So there's no contribution from the diffusion process, right? If we take them a little bit faster, this is starting to look more like a characteristic RICS dataset, right? So you have all these streaks, right? That are only one direction, as you can see. And that's because the scanning speed in one direction, in the X direction, is much faster than the scanning speed in the Y direction. So when you compute the autocorrelation function, you see that this is getting narrower, although only in one direction, because we are in a regime where this diffusion coefficient is not picked up by the fast scanning. It still appears immobile for the fast scanning. So it's not narrower in the X, but it starts getting narrower in the Y. And then if we increase the diffusion further, right? So as a comparison, 90 microsquare per second is more or less the diffusion of GFP in solution. You have all these tricks that are now much more evident than in this case. And if we compute the autocorrelation function, we basically see that along the lines, it goes to zero immediately. So this is really, really fast, the diffusion compared to the scanning. But we can see this characteristic elongation of the autocorrelation function in the X. So if we look at the individual profiles, you see that the horizontal ACF is basically unchanged if you go from 0.1, 1, 10 microsquare per second, and it starts getting narrower, but with longer tails. So it's starting to pick up some contribution from diffusion when you go to a diffusion coefficient of 100 microsquare per second. If you look along the columns, you see that you have much more sensitivity in changes between 0, 1, 1, and 10, but you basically have zero correlation when you get to 100 because it's so fast that basically decorrelates immediately. So this is useful. Why? This is useful because it gives you intrinsically a very large dynamic range in which to compute the diffusion coefficient, right? Because you can see that we're spanning over 1, 2, 3 orders of magnitude quite easily, actually. And this is barely modified. So we can actually go much faster or tweak the parameters and go much slower, right? This is actually interesting because this is basically what the sort of physiological range, let's call it, for proteins diffusing in cells is. So a fraction of a microsquare per second is typically what you would expect by something that diffuses along the membranes. And 100 is free GFP in solution, and pretty much like free GFP in the cell is more or less in the range of 10, 20, 30 microsquare per second. So these are actually quite good parameters to measure an unknown diffusion coefficient within the cell. This is basically how it translates in imaging parameters. So if you have a very fast molecule, you need at least 4 microseconds per pixel for scanning. And then it goes higher, can be longer and longer if the diffusion gets lower and slower. So the main takeaway here is that these are all very, if you have some experience with acquiring images with the laser scanning microscope, you will see that these are very reasonable parameters, right? Because these are scanning speeds that are achieved by pretty much any microscope nowadays. Pixel size is important for sampling because we want to get all these points, right, to compute the autocorrelation function. So we want to sample the point spread function enough. And it has to be a function of the point spread function. So in like assuming a sort of normal point spread function at around 300 nanometers, you want to sample it with, let's say, less than 100 nanometer per pixel, more or less, which is again pretty normal. In terms of concentration is the same, let's say, as for FCS. So in some cases, the lower the better, because you have higher fluctuation if you have less molecules, although you don't want too few molecules, otherwise you're going to have a lot of variation in the number, and then you're going to have very little photons for statistics. What I like about correlation techniques is that if you look at enough of them, you can start just looking at the function and see if your experiment was done right and start getting some sense of how to improve it. So for instance, this shows a couple of common mistakes, let's say, that you can do when you do RICS. So, for instance, you can set a scanning speed that is too low, right? So if you have a very high diffusion coefficient, but you set as low scanning speed, then basically you see you have zero correlation along the lines, right? So it's not great. So you should have some contribution along the lines. That's the ideal case, right? So you take advantage of the fact that you're scanning in 2D and you're not using only one dimension for the fitting, essentially. And then this is another example where you're undersampling your autocorrelation function, right? So in this case, it's set with a pixel size that is the same of the point spread function. And you see that basically the spatial correlations are almost impossible to see because it's not sample enough. You're getting everything in only one pixel. So I talked about fitting. Let's see an example. So this is GFP in solution, right? As you can see clearly. Okay, so RICS dataset are not very pretty images in general yet. But what we care about is the information they carry. So once you do your spatial autocorrelation function, you see that you have the characteristic line here that you can fit, and then you get the diffusion coefficient that you would expect from free GFP. But this is an imaging technique. So there are more parameters than FCS that we have to take into account. For instance, what is the size of the region that we use for computing RICS, right? So for instance, we can use the entire image, 256 by 256, and we have very little error in computing the G0, okay? So let's start from the G0. And as you can see, you can go down to one frame and have basically zero error, right? But then when it gets smaller, you start getting some error in the lower frames you take. But the real problem is that if you get smaller and smaller regions, the problem now is not the error per se, which is still pretty small, but the fact that, as you can see, the G0 gets smaller and smaller. That's because you're taking too small a region. And it basically cuts the tail of the autocorrelation function, and you're getting a skewed result. Okay, so this is important to do this sanity check and see how small can you go, let's say. And this is even more important where you're looking at diffusion coefficient, right? Because if you go from 256 to 128, it's typically all right. 64 by 64, you're getting a smaller diffusion coefficient, right? Because you're cutting the fast diffusion, the information of which is encoded in the tails, right? And then it looks like you're having slower diffusion than it is. And if you go to 32 by 32, then you're getting an even smaller and definitely not realistic diffusion coefficient. So this is very important to check the size of the region in which you compute RICS. As you see here, like the G0 value is very stable, right? So the question is, can we use it for computing some kind of concentration? Of course you can. And as you can see here, the concentration then obtained via RICS is perfectly scales linearly with the concentration that you obtain from absorbance. And you can go to units of nanomolar easily, right? So this is pretty good. Now, this is all easy. And now we go to the difficult part, which is the cells, right? So the cells, as you can see, you want to typically you want to label some protein and see what is their diffusion inside the cells. But the problem is now that the cells have, as you can see, some feature here. So you have these dots, you have more intensity here, no intensity in the nucleus, some spots here and there. So how does this translate into the spatial correlation? It's horrible because you started picking up the autocorrelation of the structures rather than the autocorrelation that comes from the diffusion. Okay, so we need to separate the contribution of the immobile fraction from the diffusion part. Okay. Luckily, we're dealing with correlation. So if you take a look at what's the autocorrelation in time of an immobile particle, you'll see that it's basically zero because it doesn't move, right? The only contribution that you have is shot noise, so we don't care about this. Spatial correlation of shot noise with no spatial pattern is zero, so this is good. So we just have basically to subtract what is the average intensity, and then we're only left, and then we're effectively removing the immobile fraction. And we're only left with shot noise that we can see it doesn't correlate, so we don't care about it. This can also be done with analog detectors, although we have to characterize it because some of the detectors have the noise from analog detectors is actually correlated over time. So there may be more corrections needed for doing this on analog detectors. Photon counting is always fine. And here is an example of what you would get if you don't subtract the immobile fraction. So you get this beautiful pattern that is due in part from the scanning and in part from to the structures in the image. So if you average all the frames that you get some intensity image, average intensity image that you can subtract from your stack, right, to remove the immobile fraction. You also have to re-add some value, which is typically the average of the entire image, in order to not have negative values, which make no sense. And then, if you compute the autocorrelation now, you're left with the correct data set, which is your contribution that is due to diffusion. Another problem that you have during time series is bleaching. So you can have, at the end of your analysis, you can have a lower intensity compared to the beginning of the analysis. This is because laser excitation can bleach the molecules. So the way to cope with this is instead of removing the entire, the average of the entire stack, you can do a moving average and then average like 10 frames, as in this case, remove it from there, and then compute the autocorrelation of the stack. Let's look at another example. So this is GFP that is attached to focal adhesion. So what you see here, these are paxillin, sorry. These are paxillin. So what you see here, these are focal adhesions. And since they have a spatial pattern, they have a messy autocorrelation function. After removal, we can see that we have our RICS beautiful and clean. And then we can feed it. In this case, it's two components, and we get the diffusion coefficient not only of the free diffusing protein, but also of the protein that is bound to the focal adhesion. So the fact that we have, depending on where we are in the image, we can get different results is clear if you consider this example, right? So if you get a region in the cytoplasm, then you will mostly get diffusion from the free form of the protein. Whereas if you go to the edges, you will get a smaller diffusion coefficient, and in other region, you're getting even smaller diffusion coefficient, all right? So spatial organization in spatial distribution of the diffusion parameters, like diffusion coefficient concentration, is important and is something that we want to take advantage of. So one way to do this is computing RICS at in small region and scanning through the image, right? And then you can have effectively a map of the G0 as well as of the diffusion coefficient, and you can get how this is distributed along the cell. Now, as you can see here, the resolution of this analysis is pretty poor because we're using very large regions. So one thing that I was working on during my PhD is doing the same thing, but maintaining the spatial resolution of the diffusion maps. And we came up with a method called local RICS, where you can effectively map. So this is the intensity image. This is the nucleus for scale, right? So even in very small region within the cell, you can effectively map the diffusion coefficient of 3GFP, so also very fast diffusing molecules inside the cell, right? And then you can tune your analysis. You can get like less frames, more frames, or a smaller region, or even a line. And this will give you much more precision in the determination of the diffusion coefficient. As you can see here, this is the nucleolus, this is the nucleoplasm, and you can see if you draw a line here, this is intensity, and the red line here is the diffusion coefficient, right? So you can see that the error in the diffusion coefficient is fractions of the microsquare per second. Another application of RICS, a bit more modern than what I showed you before, uses super resolution. In this case, STED, stimulated emission depletion, which basically has your excitation laser superimposed with a depletion laser, which effectively makes the excitation volume smaller, right? So increasing the power of this depletion beam results in a point spread function that gets smaller and smaller and smaller. This is the setup. This is pretty much a confocal setup. So you have the laser. What is this? Oh yeah, this detector. Okay. Excitation, detection, and then you get the detector, right? If you add the STED laser, what you would get here from beads, right? Now these are pretty big. And here they're super mode. So you get the single beads, and then you can also do RICS on this data set as well, right? The resolution that you can achieve depends on this saturation term that is intrinsic of the fluorophore, depletion wavelength, whatever. But basically, you can go down to like 50 nanometers or something. And as you can see here, this is, for instance, tubulin. You can get from a diffraction limited to a super resolution image. And you can see that here they achieved a resolution of around 50 nanometers, which is pretty small. Now, what does resolution have to do if you're looking at diffusing things, right? This is counterintuitive. So we're not really looking at anything if the molecules go around, right? However, if you see here, comparison with the confocal, here you have with your confocal volume, you are exciting a lot of molecules because the volume is pretty big. For a comparison, if you consider 300 nanometers diameter, let's say, but consider that the molecules are like nanometers, so you are exciting a lot of molecules. And if you have a sample that is very at a very high concentration, then the fluctuation will be really, really small, and you won't get like a clean readout. With STED, we're effectively exciting only much fewer molecules, because if you consider in volume, going from 300 to 50 is a lot less molecules that are excited. And then when you do RICS, you go from the confocal to increasing the stead power, you see that the autocorrelation function gets higher and higher and higher because you're exciting less and less molecules. So you're getting a much higher signal to noise ratio, let's say, when computing RICS. This is done, for instance, with the membrane, with the dye attached to a lipid. So it goes in the membrane, and then you see that basically without stead, you have a very noisy autocorrelation function. And when you turn on stead, you have a very clear autocorrelation function. This is the residuals. As a comparison, this is the dye that I mentioned before, AUTO647 EPPE. And then you see in these regions, you have these very noisy autocorrelation functions. But when you turn on the super resolution, you have all these regions where you can actually map the diffusion coefficient at very high resolution as well along the membrane, in the membrane, yes. So this is it on my part, the acknowledgement of all the work that's been done originally.